Hi everybody, welcome back to Chem 140. We are officially halfway through the quarter. What are we doing tonight? We are doing Unit 9. Uh-oh, what did I just do? Oh, why did that happen? Hold on. I broke my, I broke my OBS. I popped out a box and I did not intend for that to happen. And I was like, no, quick, get it back to normal. Did I hear a cat? Maybe? I don't know. Maya might be here. Oh, I definitely hear her. Okay. There she is. Oh, she was under the chair. That's why I couldn't see her. Other things that we have on the agenda, what do we got? Quiz number 4, that's Unit 7 and 8, I think. That is due Wednesday. I don't know why I'm trying to remember it. It's literally on the screen right there. But, yeah. Anyway. What is Unit 9 about? Unit 9 is about ions and ionic bonding. We're going to talk about how to form ionic compounds by first talking about how ions are formed. And then we're going to develop a pictorial way to represent this information by drawing what's called the Lewis symbol. And the Lewis symbol might be the easiest thing we do all quarter, but it's going to be very, very important, so it's worth going over. And then finally, once we have figured out how to make these Lewis symbols and then graphically shown how ions form, we're going to put them together into ionic compounds, and then close things off with a little segue at the end to lead us into what covalent compounds are. So, for Units 9 and 10, we're going to be referring to bonds a lot. And so what a bond is some sort of attraction that holds atoms together. Now, these attractive forces are quite strong. It is difficult to break bonds without providing lots of energy, or providing a circumstance where better bonds form. So chemical reactions form when bonds are broken and new bonds are formed. But the bonds between two atoms hold those atoms into whatever compound they are. Now, there's a bunch of different ways to make bonds, but they all have something in common. And that something is they all involve electrons being manipulated in some fashion. Every bond is going to involve electrons either being moved from one atom to another or placed in a certain spot relative to the other atoms, or there are other mechanisms with other types of bonding that we're not going to cover in this class because we're only going to go over 2 types of bonding, ionic bonding, covalent bonding. There are other types of bonding. There's metallic bonding, which is totally different, and we won't go over that here. We're just going to stick to these 2 because these are the 2 types of compounds we're going to discuss. So the first bonding is ionic bonding. Ionic bonding involves the transfer of electrons from one atom to another. Doing that forms a charged lattice. In other words, what ends up happening is that if I give away electrons, I make a positive charge. If I accept electrons, I get a negative charge. And then those positive and negatives attract to each other. So those are ionic bonds. That's going to be Unit 9. Unit 10 is going to involve covalent bonds. And the difference between us transferring electrons here is that we're going to instead pool them together and share them. Now, it's also worth noting that the outcome of each type of bonding is different, too. So, for instance, ionic bonds, that's not the right color. Ionic bonds form ionic lattices, whereas covalent bonds form molecules. We're going to use those terms specifically to refer to the type of bonding that occurs. So it's important that we don't just call everything a molecule because that's the familiar term. That's only appropriate for covalently bonded compounds. All right, so let's get started here. So in our atoms that we're going to use to facilitate bonding, we need to use certain electrons. And what I mean by certain electrons isn't that there's anything special about them in terms of being an electron, like all electrons are the same. They all have a negative charge. They all have the same mass. What differentiates electrons from another in terms of an atom? Well, very little other than their relative position. So if I have an atom like this, and my atom has electrons somewhere in here, I could draw a bunch of circles to represent different layers of electrons. But no matter how many layers of electrons I have, there will always be one layer that is the outermost layer. In other words, there are electrons on the outside here, somewhere in this region, that if I were to bump them into another atom, they would encounter each other and interact. The ones on the inside don't do anything. So we're just going to say that they just hang out. Only the outside layers interact with each other. And that makes sense, because if I take two oranges and I bump them into each other, it's the peel that touches and not the inside of the orange, right? The inside of the orange is relatively unharmed. That's useful because that allows us to stack oranges in a box and then ship them. And then we just get rid of the peel and you eat what's inside, right? The inside is relatively unperturbed. Now, in bonding, electrons repel other electrons, so these electrons on the outside are being pushed outside from the inner electrons. And when they encounter other atoms, those electrons should repel each other too, right? Because what's here on the outside, right here, so this is all electrons, and this is all electrons, so these should just repel each other. And they totally do. If you have two atoms that are going at a slow enough velocity, and they get next to each other, they just repel. You can actually experience this force in action on your own. Try and put your hand on the table, and then push your hand through the table. You obviously cannot do that. Just like your rear end is not pushing through the seat right now. And the reason for that is the electrons in your hand and the electrons on the table repel each other. You aren't forming any chemical bonds here because the repulsion is too great. Also because you're not moving your hand fast enough to overcome the bonds of the table or the bonds of your hand. Now, can they be forced to bond? Absolutely. You just have to make them go fast enough. And this is how chemical reactions occur. Molecules move really, really fast in solutions like liquid or air, like hundreds of meters a second. However, they don't really get the opportunity to go very far because they're just bonking into other things constantly. For example, if a water molecule in your water was moving hundreds of meters a second, it should totally launch out of your cup and like all the way into the atmosphere. But it can't do that because it's going to collide with 50 million other molecules before it does that, and it's just going to bounce all over the place. So it may not feel like molecules move super fast, but they really do. They just have a very convoluted sort of path. And when they move fast enough, they can actually overcome this repulsion on the outside electrons. And that's how bonds occur. But the important part is that it's only the outside electrons that get this opportunity. And so we're going to give those electrons a name. We're going to call them valence electrons. Valence electrons, or the outside electrons on any given atom, are the electrons that participate in bonding. So these guys on the outside here, I'm trying to color in only the outside ones, but only so much I can do with this highlighter tool. There you go. So the electrons I've highlighted in blue on the top there are the valence electrons. Now, don't worry about the number of valence electrons yet. We're going to get to that in a second. Now, the electrons that live inside are called core electrons. And I just realized, Haven't we already done this? We did this lecture last time. So all these electrons in here... I've already done this, haven't I? That's fine. Oh well. The electrons on the inside are core electrons, and they just do nothing. All we're going to care about are the valence electrons. All right. We're going to define two terms here. The first thing that we're going to define is the valence shell. And the valence shell is basically how many layers of electrons are there. So here in fluorine, this would be layer number 1, and this outer layer would be layer number 2. And so we're just going to number them from the inside going out. How many layers there are. We're going to call each one a shell. So we're going to say the valence shell is equal to what layer the outermost electrons are. And that's equal to the period number. So if you look at a periodic table and you count periods going down, 1, 2, 3, 4, 5, whatever period your element is in, that's going to be how many shells of electrons there are. So on the example here, I have chlorine is in valence shell 3 because it's in period 3. So chlorine has 3 layers of electrons. Iodine has 5 layers of electrons because it's in period 5. And you can pick any element and do this. So calcium would be layer 4, or valence shell 4. It's in period 4. Helium only has 1 layer. It's in period 1. And so on and so forth. If you're looking at the periodic table, you'll notice that as you go down the periodic table, there's more elements per row. So like in the first row, there's only 2. But in the second and the third rows, there's up to 8 if you go all the way across. And then the fourth and the fifth rows, there's 18. And then going down to rows 6 and 7, there's even more still. It's like 32 at that point. Why does it keep getting bigger? And that's because as the atom puts electrons around its nucleus, those electrons get further and further and further away. You have a bigger volume to work with. And so you can cram more electrons in that shell, quote unquote, or more specifically, the volume around the nucleus at that radius away. So that's valence shell. Valence shells get bigger and hold more electrons as you go down in period number. Now, the number of valence electrons in each shell is going to be given by the group number. So for instance, all of these elements are in group 17. We'll just do that. And what we're going to use, so there's information down here that talks about A group and B group elements. We're not really going to be using A and B group elements. So this is true for A and B group elements. But what we're going to instead do is we're going to look at the ones digit on your group for your element. And that's going to be equal to the number of valence electrons. So in other words, since all these elements are in group 17, the ones digit is 7, they should have 1, 2, 3, 4, 5, 6, 7 dots around the outside on the highest shell. So there are 7 valence electrons on all of these atoms. And you can count that and see that. Now, if I was looking at a different element, like, say, oxygen, oxygen is in group 16. The ones digit is 6. There would be 6 valence electrons. So I'd only have 6 dots instead of 7 on the outside. Everything else would look the same. So our task for the first part of this lecture is going to be, tell me what valence shell there are, how many layers of electrons, and then tell me how many valence electrons there are in the valence shell. How many electrons are in that highest shell, furthest from the nucleus? So let's do an example. For phosphorus, we're going to look up phosphorus on the periodic table, which means that I got to go to P table. So let me get that. And we got to pull that up on the screen here. So, oops. I don't know what I clicked on, but it didn't do anything. All right. So, we don't really care about the transition metal, or not transition, but lanthanides and actinides at the bottom, but they are there. All right, so let's find phosphorus. There it is, right here. Boop. So first to find the valence shell, I got to look at what period it's in. So that's just this number right here. So this is period 3. So we would say that phosphorus has... Oops, I got to change my pen here. Phosphorus is valence shell 3, which of course you can't see because I got to make that smaller. And then to figure out the number of valence electrons that it has, we look at the group number. So it's in group 15 right here. The ones digit is 5, so there would be 5 valence electrons. So think of it as like coordinates. What row is it in? That's the shell level. What column is it in? The ones digit tells you how many valence electrons. All right, so now do the same thing for oxygen, but you're going to put a minus charge on it. Okay, well, let's find oxygen first. Here's oxygen. It's in period 2, so it would be valence shell 2. How many electrons does it have in the valence shell? Well, it's in group 16. The ones digit is 6, so it would have 6 valence electrons. If it didn't have this thing right here, right? What does that little minus do? Yeah, that means add an electron. So I'm going to erase this, and I'm going to give it an extra 1 electron. So instead, it would have 7 valence electrons because of the minus charge on the oxygen. So we can still count valence electrons from the group, but we will modify it based on what this symbol is telling us to do. All right. Now I'm going to move this up here. Well, there's that in case you need it. You can always pause the video. I need to put this over... Well, we'll put it over here so we can still see the chat. What if I do this? So first we're going to find calcium. So let's find calcium. There it is, right there. All right, let's count its electrons for if it was just regular calcium without the charge on it. So it would be in period 4, so that's valence shell 4. And it's in group 2. The ones digit is 2 because it's just 2. So there must be 2 valence electrons. Now, if I want to make it plus 2, that means I have to remove 2 electrons, right? So that would be these. Can you have 0 valence electrons? I mean, that's the number we just got, right? But it turns out that if you remove all the electrons, you get an interesting situation. So I'm going to first get rid of this. We're going to go back to that picture that we just showed here. And what I'm going to do is I'm going to... I want this tool and I want this color. I'm going to remove all the valence electrons. And it's hard to do when you can't see where your cursor is, but... Here, if I do it like that, that's a little bit more manageable. All right. What do you notice is happening when I get rid of all the electrons on that layer? Because there's none left. I'm just trying to remove the entire layer there. What happened to the valence layer? It's just totally gone, right? I've removed it in such a way that it no longer exists. So the previous layer now became the valence layer. So if I go like this, it'll reappear. Boop. But if I erase it entirely, I remove all the electrons, there is no layer there. The next layer down becomes the valence layer. So we can go back to our result here. And we can say, oh, we erased the entire layer. And so what ends up happening is that this goes down to the next layer. I gotta get a color that isn't white here. Well, then how do you figure out how many electrons are on the next layer? Well, that's where you go back to the table and say, okay, what element did I land on in removing 2 electrons? Because I must have as many electrons as that, right? So I'd go, okay, here's my calcium. I go back 1, back 2. And so now I must have this many valence electrons, 8, because that's the ones digit. And so there's our answer, valence shell 3 with 8 valence electrons. The short version of that is if you ever land on 0, so like if this is ever 0, if the valence electrons are ever 0, they become 8. And the reason for that is the previous shell becomes the new valence shell. So manipulating our electrons is a little bit weird if we take away all the valence electrons. Normally we'd just be adding them and you would gain 1 or 2 electrons or whatever, and the number would just increase. So calcium is element number 20, but it is not in group 20. So remember, it's the group number, the column, that the ones digit is what we care about. So for calcium here, this is its group number right here, 2, where you can see my cursor here. You want the ones digit of that. So the group number, the ones digit, will tell you how many valence electrons you have. So only this number up here. All right, so now that you've seen it, we'll get rid of this. What I want you to do is I want you to tell me the valence shell and the number of valence electrons in each of these elements. The first 3 are elements. The second set of 3 are ions, so that's going to change the number of electrons that there are there. And then at the bottom I have xenon for some reason. We're going to talk about xenon last because it's special. So tell me the number of valence shells and valence electrons in each of these elements. We'll go over the answers in about 3 or 4 minutes. 1 or 2 more minutes and we'll go over the answers here. All right, let's go over the answers here. So, again, we'll get periodic table out. Let me find it. Boop, there we go. We'll just shove it down here in the corner. All right, so we want to look at the period number, which will tell us the valence shell, and then we want to look at the group number, the ones digit, will tell us the number of valence electrons. So for arsenic here, which is right here, that's going to be, it's in period 4, so that would be valence shell 4. And then its group number will tell us the number of valence electrons it has. So if it's in group 15, there's the ones digit, so it has 5 valence electrons. Let's do boron. So boron here is in period 2, so it has 2 shells. The valence shell is 2. It's in group 13. There's the ones digit, so it would have 3 valence electrons. And same thing for carbon. Carbon's also in valence shell 2. It's in group 14, so it would have 4 valence electrons. So I'm just trying to find a spot to put this. There we go. Now we're going to get down to the ions, where we're going to change it up a little bit. So let's find fluorine first. So fluorine is in valence shell 2, because it's in period 2. It's in group 17, so it should have 7 valence electrons. But we have to account for this minus on it, don't we? So if I minus something, that's an additional electron. So this becomes 8. Now let's go down to barium. So where's barium on the periodic table? It's way down here. So barium is in period 6, so that means its valence shell is 6. It's in group 2, so it has 2 valence electrons. But if we do this to it, I have to add 3 electrons. So this becomes 5. And then finally, potassium here. Well, not finally. We have xenon to talk about. Potassium is in period 4, so its valence shell is 4. It's in group 1, so it has 1 valence electron. But if I make it positively charged, I have to remove its electron. So this becomes 0. And we talked about what happens if you land on 0. Well, then the previous shell becomes the valence shell, and you just go to 8. And the reason we go to 8 is because, well, if I take away an electron from potassium, now I'm back here at argon. And argon has 8 valence electrons. And then finally for xenon here, xenon is in period 5, so it's valence shell 5, and it's in group 18, so it's going to have 8 valence electrons. This is all part of potassium here. So the only weird thing that happens is if you remove electrons and you end up going down to the previous shell. Just remember that if you ever land on 0, that's like having 8. And we'll be all set. Alright, any questions, let me know. Next thing we're going to do is we're going to take that information that we just got, we're going to draw it as a picture, because the pictures are going to help us understand bonding. The pictures that you see on the screen here are from the notebook of this individual. His name was G.N. Lewis. And he drew pictures using dots to represent valence electrons on the corners of a cube. You don't need to be that fancy. We're just going to draw dots around a symbol. But he did devise a method of interpreting atoms as pictorial sort of illustrations. And we can do that because it's going to be very useful to us. We're going to call this the Lewis symbol. So the Lewis symbol of any element or ion is done in the following 3-step process. Step 1, draw the symbol of the element. Whatever element it is, just write its atomic symbol. Step 2, put dots around the symbol, 1 dot per valence electron. And then step 3, if it's an ion, put square brackets and make a charge on it. So let's do that. Let's do an example for sodium. This is going to be really easy. Step 1, draw the atomic symbol. Ding, there you go. Step 2, draw a dot for each valence electron. Well, according to the periodic table here, sodium has 1 valence electron because it's in group 1. So I would just draw 1 dot. If I could get back to PowerPoint. There we go. Boink. There you go. That's it. It's not an ion, so we don't draw the brackets around it. And you're done. Easiest thing ever, right? You just have to be able to count the number of valence electrons and you're all set. So let's do that for oxygen. Oxygen has more valence electrons, right? So first draw its symbol. Boink. There you go. Then draw a dot for each valence electron. Now, if I put 6 dots around it like this, that's kind of weird, right? Because what do electrons do to each other? Well, they repel. So they're going to try and spread out as much as they can around the symbol. Now, to keep it simple, we're only going to put electrons on one of 4 sides. So in one of these boxes. And the reason that we pick 4 sides is because this mostly matches what we discover when we look into molecular geometry, which we'll talk about in 161. But for our purposes, we're just going to put electrons around the 4 sides of our symbol, one at a time, until we have to pair them. So for instance, I have 6 valence electrons, because oxygen, as you can see on the periodic table here, is in group 16. So it has 6 valence electrons. So I need to put 6 dots down around my oxygen. So here we go. Do, do. Oh, I missed. Oh, well, that's okay. Do, do. I guess the box is are a little bit off. So now I've got one dot on each side, so I'll go start pairing them. There you go. And that's the answer. So if you have more than 4 valence electrons, do one per side, and then start pairing them until you've put all the dots down. Now, what if you drew your Lewis symbol like this instead? This is different than the one that I drew down here, right? The unpaired ones are going to the left and up, but it doesn't matter. That's correct. In fact, you could put the unpaireds wherever you want to. I could do this. That would be correct. But what's important is that you're following this rule. Place one electron at a time, then start pairing them. So for instance, if you drew this instead, this would be wrong, because we did not place one at a time before we paired them. We just started pairing them whenever. And in fact, we have this whole empty side here, so one of these electrons would go down here. Doesn't matter which one. And then once you did that, now it would be correct. And then, of course, if you have an ion, make sure that you're putting brackets around it with the charge. In this case, again, not an ion, so we don't do it. So, since you've already counted all the valence electrons for all of these ions, this is the same set that you just did. Now what I want you to do is, using the number of valence electrons that you had, and I'm going to reproduce these here for you. And we'll talk about what to do for this case right here. I want you to draw the Lewis symbol of each of these atoms. Or ions. Make sure you include the brackets around it if you have a charge. So these three right here should have brackets. Alright. I'll give you a few minutes to do that, and then we'll go over the answers. Then we'll probably do for a break. 1 or 2 more minutes, we'll go over the answers. All right, let's go over the answers here. So, let's get rid of this real quick. So for arsenic, I would just put 5 dots around it. And there you go. Your pair could be on any side, doesn't matter. Boron's got 3 valence electrons. 1, 2, 3. There you go. The empty side can be any side, doesn't matter. Carbon has 4. Now, unlike the other ones, this is the only valid answer for carbon. And it's that way because we have to basically put 1 dot on each side, and I run out of dots at the same time I run out of sides, so there's only one way to represent it. For fluorine, I have 7, but I have the extra from the F minus here, so I'm going to put 7 down. The minus gives me the 8th one, and then it's an ion, so I have to put it in brackets like this. And there you go. For barium, same thing, so I would normally have 2, but the 3 minus means I have 5. And then I put brackets with a charge, and we're all set. Now I'm going to do Xenon next real quick, because Xenon is just 8. Again, there's only one solution for this one too. There you go. And so let's talk about potassium. Potassium's kind of weird, because it should have 1 valence electron, which we reduced down to 0 because of the charge. And remember that all zeros count as 8s, because the next layer comes down. So you'd think, oh, I should just do this, right? I'll just put 8 around it. And then put brackets around it. And it turns out that the convention for this is actually just to leave it at 0 and not draw any dots at all. So that's a little strange, but whenever we have an ion that removes all of the electrons and you land on 0, the convention is to just draw 0. Now, how many valence electrons does it have? It actually does have 8, because you can't have 0 valence electrons, right? There will always be a valence layer. So it's sort of a semantics thing versus a practical, what makes sense to draw thing. And that's the convention that we've just decided upon is, oh, we're going to draw something that has no valence electrons because we removed them all as just having nothing around that. And you're going to see why that is in the next section when we start putting these atoms together to try and figure out how to make ionic compounds out of them. But that's going to be after the break here. So I'm going to put the music back on. I'm going to go run and have a snack because I'm starving. And I'll see you in about 10 minutes. Alright, we're back. If you can guess the theme of that last track, it was meant to be underwater. I mean, that's... When I go swimming or whatever, that's the song that plays in my head, because this entire game is ingrained in my, like, very, very being. Alright, so... Now, on the last slide, which I actually clicked away here, but we'll just go back to it really quickly here. So if you look at Xenon down at the bottom, Xenon's kind of special. And you'll notice that by our rules that we have used to figure out the Lewis structures of stuff, there should be nothing that we can do to make our atom have more than 8 valence electrons. Like, 8 is the limit here. There's only space for 8, because our rule said do 1 then pair, remember, when we're going around the outside. So if we had a 9th one, where would we put it? And the answer is, well, we never have to worry about that, because looking at the periodic table, which... Will this show up again? No, it didn't capture it. I gotta find my window again. Hold on. Oh, that won't work. Hold on. There it is. Boop, there you go. You'll notice that if I go like this, it doesn't go any further past 18. There's no 19th group, so I can't have 9 valence electrons. Instead, what happens is, if I try and add a 9th valence electron, it just ends up going to the next period. So 8 is the limit. And it's the limit because it's stable. So if I hit 8 valence electrons, I reach an interesting condition. All of the noble gases are 8 valence electrons. Also, all of the noble gases are very stable. They don't react with the stuff. They just hang out, right? And so that ends up conferring a very important property when we're discussing ionic compounds. And that property is that, hey, things will react, but not if they end up with 8 valence electrons. So this is called the Octet Rule. An atom is stable, or more stable at least, if the result of its interactions with other atoms leads it to have 8 valence electrons. So, in other words, in order for something to never have to react at all, it has to automatically start with 8 valence electrons. So, only the noble gases do not do any reactions. All of the other elements have fewer than 8 valence electrons, and what they will do is they will react in such a way that they get 8 valence electrons, and then they're stable. For instance, this chlorine gas is extremely reactive and deadly. This is like one of the components of mustard gas. If you breathe chlorine gas, it will oxidize your lungs and you will die. However, if you eat this, which we do every day, because it's part of table salt, nothing happens. In fact, it's just delicious. Chloride is very safe. It's abundant in your body. It's necessary. Not necessarily as a nutrient, but as just like a charge balance. And the only difference here is just this last electron. So there's nothing here, but there's something here. So this one's deadly, and the other one is perfectly normal. The same is true with, like, say, sodium. Sodium has 1 valence electron, and it will explode on contact with water. So the second you put sodium metal on, like, say, your tongue, boom. Not what you want, right? Not a good start to your day. But if you take away its electron, it now has an octet from the previous layer. And instead of being explosive, it's now just delicious. Totally safe to consume sodium ion. Do not consume sodium metal. So there's a vast difference between the element form, which does not have an octet, which does not have 8 valence electrons, and the ionic form, which does have 8 valence electrons. So that's where we're going with this. And again, remember that if you have 0 valence electrons, it's the same as having 8 valence. So that's the octet rule. We want to get to an octet. If you don't have an octet, react with something until you do. So our job is going to be to pair elements together so that they react in such a way that they all achieve octets. Because once everything is reacted, everything is stable, and the end result is what we would observe. Oops, I hit a button. Oh, I just hit plus, that's all. Okay. Alright, so here's oxygen. Oxygen does not have an octet, so this oxygen atom is reactive. It will either give away its electrons or take electrons to get to an octet. What is the most likely result to occur based on what you see here? Well, if my goal is to get to 8, then the easiest thing to do would just be add 2 to it. And so we'll do that. And then we need the brackets, which I don't think this puts in there. There we go. Yeah, don't forget to add the square brackets. Boop, there you go. So you can see here that we're taking our neutral elements and making them into ions by changing the number of electrons they have so that they have an octet. Let's do the same thing with calcium here. Calcium, we're going to remove its 2 electrons. And by doing that, I end up with 0 valence electrons, which, remember, 0 counts as an octet, because the previous shell is implied to be there, but we don't draw it. Now, alternatively, I could have done something like this. But what's easier to do? Add 6 things or remove 2 things? Since there's far fewer steps in removing 2 things, that's the step that occurs. So there's always a choice to get to an octet. However, nature is lazy. Nature will always take the easiest option because that's the one that requires the least amount of energy. So if you aren't sure which direction to go to get to an octet, remember, go in the direction that is the shortest. So 2 is closer to 0 than it is to 8, so we're going to get to 0 electrons, which counts as an octet. 5, on the other hand, is closer to 8, so we're going to gain electrons until we get to 8. We're not going to lose 5. Too much effort. Choose the path of least resistance. Alright, so to summarize, things that have few electrons will tend to want to give them up. So that includes things like the metals. Elements in groups 1 through 13 have very few electrons. And let me write the actual numbers here. So 1 through 13. They tend to have very few electrons, and so their objective is to just give away their electrons so that they become an octet with 0, in other words. Nonmetals, which are 15 through 17, have a bunch of valence electrons. They need to get to 8 anyway. They're most of the way there, so they accept more. Noble gases already have octets. They don't do anything. And then, of course, there's a weird exception, and that is, what do you do about the thing in the middle? So I have carbon. What's faster to get to? 0 or 8? Well, I'm at 4. I'd have to lose 4 or gain 4 in either case. So what does carbon do? Carbon decides to strike out on its own, and it does everything and anything that it wants to. And there are so many weird options because carbon is right there in the midpoint. that we spend an entire year talking about what carbon is capable of, and that's called organic chemistry. So if you're in biology, you get to take OChem, and you can look forward to that in 261, 262, and 263. We're going to talk about it very briefly in Unit 10 so that everybody gets to enjoy carbon chemistry. But only the biologists and chemists are actually going to go on to take 261 through 263. Or material science engineering, or maybe chemical engineering. So, depending on your engineering, you don't have to do that. Alright, so what I want you to do is, using these symbols down below here, so this question actually refers to these, I want you to draw the Lewis symbol, and then predict the ion that should form. So add or remove dots, and then predict the charge. So for this first one, for chlorine, for example, this is what chlorine looks like. To get to my octet, I have to add one extra electron. So I would predict this is the charge that forms. Okay? Do that with all the other elements. Don't worry about how many protons and electrons this has. We'll talk about that later. And then down here, I've drawn a bunch of symbols. Tell me which ones are stable. That is, which ones have an octet. Circle those, and then draw an X through the ones that are not stable. Okay? Draw an X through the ones that do not have an octet. Now, be careful. Make sure that the octet that those atoms reach is the simplest path. Okay? Otherwise, that's not the ion that would form. Alright, I'll give you about 5 or 6 minutes to do this. We'll go over the answers in a bit. 1 or 2 more minutes, and we'll go over the answers. All right, let's go over the answers here. All right, so we'll start with drawing the expected ion. So I already did Cl, so that's Cl minus. We'll just write that down. Oh, there we go. It took a second to appear there. I'll draw its Lewis symbol out here, so there you go. And then we would shorten that to just look like that. If we weren't drawing a Lewis symbol, for example, if you just wanted to represent that like in text, you would just put Cl minus. For barium has 2 valence electrons, so what I'm going to do is I'm going to erase both of them. And that's the ion that would form, is barium 2+. How about nitrogen? Nitrogen has 5 valence electrons, so I need to put in an extra 3 to get to my octet. There you go. I don't always circle these charges. I just circle them so that you're aware, oh, it's a charge. You don't have to. So let's look at sulfur here. Sulfur has 6 valence electrons. So it looks like that. I need an additional 1, 2 of them to get it to its octet. And there's the ion that forms. How about phosphorus here? Phosphorus has 5 valence electrons, so I got to give it 3 more to get its octet. And rubidium here has 1 valence electron. We're just going to kill that right now. Boop. And that's its octet there too. Now you could do the exercise if you'd like for how many protons and how many electrons does each ion have. That exercise is just so that you're counting the total number of electrons. So remember, there is a distinction between valence electrons and total electrons, because total electrons would be all your valence plus all your core. So we're not going to do that, just in the interest of time here. Oh, I should just go back to this screen, actually. So for the bottom set, Circle the ions that are expected to be stable. Draw an X through the ones that are not. So let's look at the elements just one by one. So what would aluminum be? Well, aluminum has 3 valence electrons. If I get rid of those 3 electrons, it will have an octet, and it would be +3, so this must be stable. Does it matter if you put the negative and positive before or after? So the convention is that the number comes first and then the charge. If you do it the other way around, it sounds like a magic item from Dungeons and Dragons, and I guess other scientists will laugh at you about that. Technically, it's fine either way, because it conveys the same information, but the convention is to do the number first. On Canvas, if you do them in the wrong order, it will get marked wrong, because Canvas is stupid and it only follows, like, if I type in the answer is 2+, it will only accept 2+. And I don't go through and program it to accept all the, like, +1, +2, +3, whatever. So on Canvas, you do have to put the number first before the charge. But on paper, like, it's fine. Everybody will know what you're talking about. If I look at selenium here, selenium has 6 valence electrons. To get to its octet, I'd have to give it 2 more electrons. So that's the charge it should form. How about bromine? Bromine needs 7, or bromine has 7 valence electrons, so it needs 1 electron. But remember, when you give something electrons, it becomes this. This has a plus on it, so this isn't what forms. That's just trying to trick you. So be careful. Don't mix up the positive and the negative signs. When you have a negative charge, you are adding electrons. When you have a positive charge, you're taking them away. Here's calcium. I'm going to get rid of its electrons to make it an ion. Hey, that worked out. Here's phosphorus. Phosphorus already has 5 electrons. And you can probably see what it's trying to do here in this tricky question here. And you would say, oh, I'll just get rid of all 5. That's an octet. But the easier way to do it is to add 3. Oops, 3 minus. Darn it. Pen slipped there. So this is not the one that forms. Because 3 minus is easier. Moving 3 electrons is easier than moving 5. And by a similar path, you can figure out arsenic. So arsenic is 5 also. We're going to give it 3. That was supposed to be an electron. So that's good. And then cesium, with its 1 electron, if I get rid of it, becomes that and not minus. So be careful on how you arrange and organize your electrons here. All right, so the last thing we're going to do for this section is I'm going to put this note up here that the octet rule that we've been following for this only really works for main group elements, and what that means is it says groups 1A through 8A, and this is where the A notation comes in. That's actually handy. And so this translates to groups 1 and 2 and 13 through 18. So groups 3 through 12 in the middle of the periodic table, those do not follow the octet rule or anything that we've talked about today, actually. Transition metals are weird. They follow their own sort of different rule set that we're going to go over in 161 when we talk about electron configuration. Here, we're just trying to find and establish a basic pattern. And the basic pattern is the number of valence electrons is the ones digit of the groups, but only of these groups. So what does that mean? You can make any ion you want to. I could remove 4 electrons from, say, titanium. But in doing so, I won't land on an octet. So later on, when we start making ions out of things like transition metals and stuff like that, we're not going to know what the charge of the ion should be because it doesn't land on an octet. However, for these elements that do, we can always predict their charge using the Octet Rule. So if your element is in these groups, and again, that's 1, 2, and 13 through 18, use the Octet Rule. In fact, you have to. If your element is not in one of those groups, use the Octet Rule on the other elements who are in those groups, and then use that information to solve the problem. You'll see what I mean by that later on. But for now, we're not going to draw Lewis symbols for anything in groups 3 through 12. I'm just going to tell you the symbol, and there will be some context in the problem that allows you to solve for the charge. And again, we'll get to that later. It's just that I don't want you thinking, oh, I can apply this to absolutely anything. It only works for the groups that I've shown above, 1A through 8A, which are, again, 1, 2, and 13 through 18. All right. So the last thing we're going to do today, because we only have, 15 minutes left? Yeah. We're going to talk about how we create ionic compounds using this notation, because we know the idea. The goal is to get an octet on everything, and not everything has an octet. So we need to move electrons around in some capacity. How do we do that? First, the premise of making an ionic bond forms when I have two charged entities next to each other. Okay, that's cool and all, but how do the charges form? What are the patterns? Well, remember, moving electrons off of something makes it a cation, and adding electrons to it makes it an anion. So, adjusting the number of electrons something has causes it to become charged, and that is the first step in making an ionic compound. Once I have made the charges on two different things, if I put those charges next to each other and they're opposite, they then stick to each other, and I create an ionic bond. And so the attraction between opposite charges is where the ionic bond comes from. All cations are attracted to all other anions. They don't care about what the identity is of the cation or the anion. It could be calcium, it can be sodium, it can be anything. All positive charges attract to all negative charges. Now, what does that look like? When I form my bonds, my ions are going to attract to each other like so. So these will be attracted, and they will join together and basically be stuck. But charge does not just go in one direction. Charge goes in all directions. And so what that means is that in any of these positions, a negative will move in and be attracted to it. And then for each of those, a positive will move in and be attracted to it. And this repeats over and over and over and over and over again until you generate your lattice. And this is what your lattice is right here. This is the Ionic Lattice that we generate. In the Ionic Lattice, the simplest repeating pattern, in other words, what can you circle and highlight with your mouse, hit copy, and then go paste, 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 paste. That unit is called the formula unit. So the formula unit is the simplest bit that repeats over and over and over and over and over and over again. And you can see that I've circled a chlorine and a sodium. You can just paste that on a diagonal over and over and over and over and over again. In reality, it's a little... I'm simplifying it a lot. There's something called a unit cell that you copy, which is a cube that takes out fractions of atoms, and you can line them all up and paste that over and over and over again. But the idea is more or less the same here. To make an ionic compound, you take your formula unit and you just repeat it over and over and over again. Now, because ionic compounds form lattices, these are not molecules. Formula units and molecules are distinct. Alright, that's formula units. This is what ionic compounds look like once they have their charges on here. And you'll notice that the charges are already present. So these are all plus, sodium pluses are the purple, and chloride with the minus is the green. So we know the end goal of how to make an ionic compound, but how do I do this out of elements that are neutral? So let's suppose that instead of sodium with a plus and chlorine with a minus, instead I tried to mix these two together. Just regular old sodium and regular old chlorine. Will they react with each other? Will they stick to each other? Currently, they don't have charges. So they would just look at each other and be like, huh? Or would they? And the answer is, well, we have a video for that, so that's what we're going to watch. Let's show the formation of sodium chloride in the laboratory. All right. So this is Lonnie. Lonnie's kind of creepy. I only say that because I think he's a professor at Berkeley. But I don't know if the close-up is doing any favors. Like, ooh, that is creepy, right? All right. We're going to watch in his lab here the formation of sodium chloride. He looks less creepy when he's actually doing his experiment. All right, so what he's going to do is he's going to take this container right here of chlorine gas and subject it to hot sodium. Now, you can kind of see that when he puts something behind him, or behind the container, I don't know what my cat is going on about. That wasn't Maya, that was the other cat. That was Kresnik, sorry. You can kind of see right here that it's a little bit yellow. That's the chlorine gas in there. Chlorine gas is a very faint yellow. In the bin over here is sodium metal. Sodium metal is stored under a mineral oil. And the reason for that is because, as we saw at the very, very beginning of class and at the very beginning of the quarter, it reacts with water very quickly. So he's going to put in another sample of hexane to rinse off the oil. Hexane itself will burn off really quickly when he puts it in this flame over here. Next, he's going to take his sample of sodium. He's going to put it in this little ladle. He's going to heat the ladle with the sodium in it until the sodium is molten and starting to melt. That's going to give it enough energy to start the reaction with chlorine. So that bright orange you're seeing right there is the hexane burning off. Then that deeper orange that you see there is the sodium itself igniting. And then once it's hot enough, in it goes. And this happens. Now, Lonnie's really safe here because this experiment is set up over a fume vent. So you can see all the gas that's escaping being sucked straight down. So he doesn't have to worry about breathing chlorine gas. He's going to be fine. But inside the container, the elemental sodium and the elemental chlorine are reacting and forming something new. And that something new that's forming is ionic sodium chloride. So this reaction is just shuffling electrons around. And once it's done, you can see how hot the ladle is, by the way. This reaction is very, very energetic. Once this is done, and all of that stuff inside coalesces down, what you will get is this. This is table salt. The color looks a little bit murky, probably because the chlorine gas in the container is just... Like, he uses this container specific for chlorine, so it's stained. But the substance that you get at the end will condense down into a white solid and become table salt, and you can actually eat it. Although you probably shouldn't do this in the laboratory. Like, Lonnie, this is not lab safe. But yeah, you totally get sodium chloride, which is table salt, that you can eat, and it's delicious. And he's very proud of his egg, breaking lab rules. Bad Lonnie, no biscuit. So we saw this in action, but what specifically happened for us to get from sodium and chlorine to these things? And the answer is, well, we just shuffled electrons around. If sodium has 1 valence electron and chlorine has 7, and both of them want an octet, there's a really easy solution here. Sodium does not want this electron. Chlorine wants an extra electron. What if I just bump it on over? And in doing that, I now have these structures. And those structures both have octets, so they will attract to each other to form an ionic bond. So our objective in making ionic compounds is very straightforward. Move electrons around until everything has octets, and the result is your ionic compound. And this is actually where we're going to start next time. So tomorrow night, we're going to stop a little early tonight because I think that we're kind of... I don't want to get knee-deep in a topic and then go into, like, 7:05 or something. But what we're going to do tomorrow is we're going to start pairing elements together. Like this. So let me just show you some examples here. And we're going to make ionic compounds out of them just by moving electrons around. Okay? So go ahead and look over these slides tonight. We're going to review a little bit of this tomorrow, and then we're going to finish off Unit 9, because Unit 9 is not very long. We'll start Unit 10 tomorrow. And we'll talk about covalent bonding, which also uses Lewis structures at that time. And there's something... Ow. I stepped on something, and that was not pleasant. It's like a rock or something. All right. Yeah, that's really all I have. So, I don't really have much else to say other than I think tomorrow at some point we will be going over the lab material. So make sure that you check out the lecture slides for that. Or not slides, but the lecture stream for that. And yeah, I got nothing. So have a good night. We'll see you tomorrow. We'll finish up Unit 9. Make sure you get quiz number 4 due by Wednesday.